Olá a todos que nos acompanham ao vivo pelo canal do GIEM no YouTube e aqueles que em outro momento assistirão a essa conferência. É com grande alegria que damos início a mais um seminário de pesquisa em educação matemática, uma iniciativa que vem sendo construída com muito compromisso e colaboração desde 2016. A conferência que assistimos hoje, proferida pelo professor Carl Winslow, da Universidade de Copenhagen, Dinamarca, faz parte de uma trajetória iniciada há décadas pelo Departamento de Matemática da Universidade de Brasília, que, desde os anos 1990, promove palestras, oficinas e seminários sobre o ensino de matemática, reunindo professores, formadores e pesquisadores do Distrito Federal, do Brasil e também do exterior. Ao longo dos anos, essa ação se fortaleceu por meio de parcerias com instituições como a Sociedade Brasileira de Educação Matemática, a Sociedade Brasileira de Matemática, o Instituto Federal de Brasília e a Secretaria Estadual de Educação do Distrito Federal, entre outras instituições. Em 2019, os seminários passaram a integrar oficialmente os projetos de extensão do Departamento de Matemática da UNB, com o apoio da graduação, da pós-graduação e de diversos grupos de pesquisa. Em 2020, diante dos desafios impostos pela pandemia, os seminários se reinventaram, passaram a ser transmitidos virtualmente, ampliando seu alcance. Hoje, com uma programação híbrida, presencial e online, continuamos a promover a formação docente, o compromisso com os processos educativos, o debate acadêmico e a socialização de pesquisas que impactam o ensino da matemática, da educação básica e ao ensino superior. Os seminários de pesquisa se consolidam como um espaço inovador, plural e formativo. E vocês fazem parte disso. Sejam muito bem-vindos à conferência de hoje, de 27 de junho de 2025. Participem, comentem, compartilhem e ajudem a divulgar esse espaço de construção coletiva de conhecimento. Agradeço ao professor Carl Winslow pela partilha de hoje e à professora doutora Aluska Macedo, os quais convido agora para tomar lugar neste espaço virtual. Sejam muito bem-vindos.
Obrigada, professora Adriana. Welcome, Professor Carl Winslow.
Thank you.
Agora eu vou apresentar o professor Carl. Graduou-se em matemática na Universidade de Odense em 1991. Atuou como assistente de ensino em matemática e física na Universidade de Odense. Concluiu o mestrado em matemática e francês na Universidade de Odense. Foi bolsista do Conselho de Pesquisa, incluindo período como pesquisador visitante no Departamento de Matemática da Universidade de Copenhagen, em Berkeley, de janeiro a julho de 1992, estudos de doutorado no Departamento de Ciências Matemáticas da Universidade de Tóquio, sob a orientação do professor Yasuyuki. Obteve o doutorado em Ciências Matemáticas pela Universidade de Tóquio em 1994, trabalhou como assistente na Universidade de Copenhagen de abril de 94 a janeiro de 98, foi professor de pesquisa associado na mesma universidade, atuou como professor associado na Universidade Dinamarquesa de Educação, tornou-se professor titular com funções especiais na Universidade de Copenhague de agosto de 2003 a outubro de 2007 e desde 1º de novembro de 2007 é professor titular na Universidade de Copenhague. Presidente do Grupo de Pesquisa Didática da Matemática da Universidade de Copenhague. Desde 2021 é o presidente da Sociedade Europeia de Educação Matemática e membro do Conselho de Estudos de Matemática e Ciência da Computação da Universidade de Copenhague desde 2022. Now you can start your talk. Thank you.
Thank you very much, Aluska, and also the team of hosts for organizing this lecture. So I understand there are several teachers among us, and that's very good because in some sense what I will talk about is only makes sense because we have schools and we have teachers teaching mathematics in schools. And those who teach mathematics in school will be aware that teaching mathematics is not so easy. Learning mathematics is not easy for all children. So I think in every country around the world, Denmark, Brazil, every country, teachers will recognize the situation that you have children for whom mathematics is almost impenetrable and hard to learn, and so on. And this is not a new situation. And of course, sharing ideas from various parts of the world, what we can do. So there's a so what we can do to help teachers and students with the learning, teaching and learning of mathematics, sharing ideas from different parts of the world is very valuable, because the problems are often quite similar from one country to another. So the reason I will present some European approaches, as the title says, is not that we have solutions to all problems, but in the spirit of sharing ideas and approaches across continents, and at some other occasion, I'm sure I could also learn a lot from the approaches and experiences that you have in Brazil. But so today we will look at Europe, this continent across the Atlantic Ocean. And I will talk about two, I think you could say, major European traditions in research on mathematics education, also what we in Europe called didactics, namely the German tradition. In German, the word is Didaktik, but it's the same word in all European languages except English. We have such a word in Danish, it's Didaktik, so it's virtually the same. And the other grand tradition is the French, and in French it's called didactique, but you can say it's exactly the same word. Didactique or didactique comes from the Greek verb to teach. So it's the study of conditions and methods for teaching something. And when we say didactics of mathematics, we mean the specific study of how to teach mathematics in a good way. And you can see that these two traditions are of various age. The German didactic has very old roots that I will also explain in a minute, going back to Felix Klein. Yeah, you should put the, yeah, like this. Yeah. So going back to Felix Klein, I will talk about that, and then it developed in the 1960s to what is now called Stoffdidaktik, which means subject matter didactics, or the specific study of mathematics for teaching, if you want to translate it, with figures like Kirsch and others from the 1960s. And on the other hand, the French didactique, which may be better known to some colleagues in Brazil, because many French people have also visited Brazil over the years, and some Brazilians also went to France to do a PhD and so on. So I think maybe this part will be more familiar to some of you. But in France, we have the tradition of the theory of didactic situations in mathematics developed by Guy Brosseau from around 1970. And a little bit later, as a kind of continuation or extension, elaboration of the theory of situations, the ATD, or anthropological theory of the didactic, that was mainly developed, especially in the beginning, by Yves Chevalard from around 1980. Chevalard was, by the way, doing his PhD with Guy Brosseau, so there's a clear connection also between the two. Okay, so this is the program, so to speak, and I will start by the historic roots and the background to all of this, perhaps also to explain that some of these ideas are quite old. So the first thing that to make clear is that in Europe, that is a continent that consists of many different smaller countries with each their language and so on. The development of schooling has been also quite variable, but in all of the countries, compulsory primary school education was established before 1900, so meaning everyone went to school, and also in those public schools there was mathematics, but it's as a history which is quite different. So in Prussia, which is part of what is now called Germany, already this was established in 1717, so almost 200 years before. The German-speaking countries were very early with establishing public education. In France, this comes a little bit later as a consequence of the French Revolution. So the idea that every citizen needs a certain basic education. In my own country, Denmark, it's much later. 1837, there's the Acts of the Public School, and in other countries it's even later. So, so there are national histories of the public schooling, and also different speeds by which mathematics was progressively becoming a subject taught to everyone. It was, of course, in public school, which means primary school, roughly basic arithmetics to get by in daily life of a citizen, and also often a bit of practical geometry, measurements, forms, and so on. Secondary schooling, on the other hand, from age 10 and up, it also has a long history. The first secondary schools go back to the so-called Latin schools, where people prepared for university, but it was very elitarian, and only much later became extended to larger parts of the population. That is what we see in the 20th century. But in any case, and of course, secondary schooling has generally much more emphasis on more, let's say, properly mathematical topics like algebra, geometry, and so on. And you can say that research in didactics of mathematics in all European countries arose out of the need of training teachers to teach mathematics, especially at the secondary school. And at university, they would then generally prepare for that in a mathematics degree. So didactics of mathematics is to provide part of the contents for such a mathematics degree for teachers. One of the first to explicitly reflect on this new task of universities to prepare teachers to teach mathematics is the famous German mathematician Felix Klein, whom any mathematician will know, for instance, for the Klein-Vier-Gruppe or the Klein bottle and so on. He's one of the really famous mathematicians, also from the first part of the 20th century and before. But it is not so well known by everyone that already in his inaugural speech, so the talk he gave as he ascended to the position of professor at the University of Erlangen, he exposed his views on mathematics teacher education almost in a programmatic way. And here I quote from the English translation of that talk, which was of course held in German, an English translation, and where he said, for instance, and he come up with this idea of mathematics from a higher viewpoint. So he writes, or he said, we as university teachers require not only that our students on completion of their studies know what must be taught in schools. We want the future teacher to stand above his subjects, that he has a conception of the present state of knowledge in the field, and that he generally be capable of following its further development. But this higher task also requires improved instruction at the university. So for Klein, it is a question of improving instruction at the universities to prepare teachers for looking at teaching tasks with the aid of the present state of knowledge in mathematics, and also to keep that knowledge up to date, alive, and so on. And we all know how difficult that is today, where mathematics is such a highly developed area. But this was his first thoughts on this, and then then he wrote towards the end of his career in 1908 a book, or actually a book in 3 volumes, where he exposed his more mature view on this task of preparing teachers, and especially to prepare them mathematically to teach. And this is the famous book in German. The title is Elementarmathematik vom höheren Standpunkte aus, and that means in English, as the title says, elementary mathematics from a higher standpoint. It's a book in 3 volumes then, where he exposes school mathematics, but from this higher viewpoint of university mathematics, which the students would have acquired during their time at university. It's a really very interesting and valuable book for teachers even today, especially maybe, well, some parts are relevant for primary school teachers, and much of it is still relevant for high school teachers. And here's a famous quote from the prologue that also indicates how Klein's idea of this higher viewpoint had developed. It's a very famous quote from the prologue, explaining further his aim, with a little story. At the beginning of his studies, the young student is faced with problems that in no way remind him of the mathematical things he worked with in school. Naturally, he then forgets these matters quickly and thoroughly. If he becomes a teacher after having finished his studies of mathematics, he must suddenly teach this time-honored elementary mathematics in a school-like fashion. And as he cannot by himself see the connection between this task and university mathematics, his university studies become just a more or less pleasant memory, which has no influence on his teaching. I think many teachers, perhaps also teacher educators, will recognize this that dilemma, that you can have learned quite substantial amounts of advanced mathematics and not necessarily see the connection between that advanced mathematics and your task as a teacher. So Klein's goal in these books is to demonstrate how the higher viewpoint coming from advanced mathematics can be an assistance to the teacher who wants to develop and make his teaching more live. We come back to that also with this last quote from Klein, but Klein is really always worth reading from this lecture course for future teachers that has inspired many capstone courses and so on. So he says, my task will always be to show you the mutual connection between problems in various disciplines of mathematics. These connections was not sufficiently considered in the specialized lecture courses, so standard university courses, and I want more especially to emphasize the relation of these problems to those of school mathematics. This way, I hope to make it easier for you to acquire that ability, which I look upon as the real goal of your academic studies, or of the teacher's academic study, the ability to draw in ample measure from the great body of knowledge taught to you here as a vivid stimulus for your teaching. So, in other ways, after having completed advanced studies at the university, the student must restudy elementary mathematics from this higher point of view, and to help students doing that, mathematicians must do the same, restudy elementary mathematics and doing that, preparing the teachers for teaching. So in other words, this is a vision of teacher education very much linked to advanced mathematics, to scholarly mathematics, but recognizing also that scholarly mathematics is not sufficient. It has to be prepared and elaborated by the students after their main academic study. This is also, in a way to show the passage from Klein to modern Stoffdidaktik, except there's of course a long time from the death of Felix Klein. Felix Klein deceased in 1925, and then to modern didactics. So I jump a lot of things here where the German school of thinking in mathematics for teaching continued to develop to some extent, but of course with a huge break due to the two world wars. So Klein's work from 1849 to 25 is kind of an early version of Stoffdidaktik, emphasizing the double discontinuity problem. And also Klein was responsible for introducing functional thinking as a core element of upper secondary school mathematics. He insists that advanced courses in mathematics do not suffice to train secondary mathematics teachers, but that a link has to be established between living mathematics, so contemporary research mathematics, and school mathematics. And also he is, as I said, the guy who introduced functions as core element of secondary mathematics, not the Euclidean geometry as before. And you can say that he represents an early version of Stoffdidaktik, for which didactic or the didactics is really an integral part of mathematics at university. Okay, so following the Second World War, we have this, well, actually a little bit before the war also, but we had have a group of mainly French, but with time also mathematicians from other countries who developed a new, let's say, foundation first for the science of mathematics, and then especially with this the guy as a front runner, Jean Dieudonné, a French mathematician, also the idea that school mathematics should follow this more modern approach to mathematics. So the Bourbaki group developed first as long series of publications on this, how to present and found mathematics as such. And then Jean Dieudonné was among these, but also a frontrunner for this modern mathematics reform of school mathematics, where according to which axiomatic methods, logic, set theory, and so on should be at the beginning even of school mathematics, not only lower secondary school, but even in primary school. I remember myself having been to school in the 70s that we had more sets than numbers in the very first classes of primary school. And then, of course, came a reaction also in the 1970s against this, because it was a very difficult curriculum for teachers and perhaps also pupils. So that led to the creation of several European schools of research and didactics of mathematics in order to come to grips with how this reform could be modified or perhaps substituted by something that would be less problematic for schools. In Germany, that led to the second, you could say, generation of Stoffdidaktik, the modern Stoffdidaktik from 1970 onwards, with people like Kirsch and Griesel, whom you see to the right. So it's not it was not a creation of one person, but there were several grand figures in this up, let's say, flourishing of German Stoffdidaktik. So among the slogans, also as a reaction to modern mathematics, mathematics must be sachgerecht und kindgerecht, meaning right on the matter and right for the child. So it's not enough that your curriculum is appropriate mathematically, it must also be adapted to what children can learn. It's strongly related to the tradition going back to Felix Klein, but unlike it is not purely theoretical or purely mathematical, but attempts also to base curriculum reforms on observation and experiments, and is perhaps even more than Klein, deeply involved in creating curriculum, so programs, textbooks, and so on, in the German-speaking parts of Europe. So that is, in fact, the declared purpose, to support curriculum development, and of course also, as was Klein's idea, to support the preparation of teachers to teach mathematics. But as I said, it's not purely mathematical. It is also highly inspired by cognitive theory. So you could say ideas coming from more mental models of learning, and a very central notion in most of modern Stoffdidaktik can be credited to Griesel, is the idea of Grundvorstellung, or basic idea. And he also explains this basic ideas as ideal mental representations. So the representations of a piece of mathematics that students should have in order to, let's say, understand the meaning of the notion and not just its formal character. So just to take an example from a recent paper by Grefrath and other colleagues, the limits of a function. There are several basic ideas, but two different basic ideas of limit is, for instance, the approaching movement of the function as so the function approaches the limit as the arguments, often called x, approaches the point A. So as the argument approaches A, the function approaches I. So you have this is not a formal definition, of course, but an ideal, one of several ideal meanings that students should attach or associate with limits of function. Another one is the neighborhood basic idea, which means that f of x goes to A, the meaning is that in the vicinity of A, the function is close to the limits. Stoffdidaktical treatises on topics, among other things, lay out such basic ideas, meanings of elementary mathematics to be taught in school, which teachers should know, because they should be aware of the importance and functions of these meanings in the learning of the mathematical topic. So, of course, that doesn't mean we should just teach such images or ideas of mathematical context. At the same time, there are also formal mathematical ideas, or also often called aspects of mathematics, and these may link in various degrees to different basic ideas. So that is one important reason why students should develop several basic ideas of a central notion like the limit of a function, that they can support various formal aspects of the notion in different ways. So, for example, the following definition, which I learned in the second year of high school, is very close to the neighborhood basic idea. So this is the formal definition, that for all epsilon there exists a delta, and so on. That so that when x is or x is delta close to a, then f of x is epsilon close to L. So that gives the idea that near, if we are near a, delta near a, then f of x is epsilon near L. So that is clearly a definition which is closely related to the neighborhood's basic idea. The approach basic idea, on the other hand, is supported both by graphical representations and can be misleading for the general notion, by the way, because you can have the wrong approach idea that a function goes to L means that f of x approaches L without ever reaching it, so a kind of asymptotic limiting, but this is of course very partial and sometimes incorrect meaning. So modern stuff didactics is still to a large extent an elaboration of elementary mathematics for teachers, explaining not only the various concepts and the structure of the elementary mathematics, but also the meaning, its different meanings, and exemplifying how you can develop these meanings in actual teaching. So that is something which also today is a main ingredient in teacher education in German-speaking countries, but I would say largely unknown outside of the German-speaking world, but really worth studying. And I mean, just beginning by studying Klein can be a way to access this world of thought if you're interested. Okay, so now I will shift to France. And delve directly into Brousseau's research program, which is also in a way a research program that is really relevant to teacher education, because the perspective of the theory of situations is really close to the perspective of the teacher. So it was founded by Guy Brousseau around 1970. He was actually a primary school teacher first, and then he was in various ways became interested in this idea of developing a scientific approach to mathematics teaching. So he studied mathematics and then got to lead a French National Center for Research in Mathematics Education, the COREM, and also related to this network of IREMs that were found all over France from 1970 and still exist at every French university, so institutes for research on mathematics education, or didactique des mathématiques, as they say in French. So the theory of situation aims at developing a fundamental science, so not just some applications of mathematics, but really a science in itself, on the teaching and learning of mathematics, based on a very strong theoretical paradigm and an equally characteristic and strong approach to experimental work with mathematics teaching. It assumes the classical idea of Piaget that learning takes place in situations. So the notion of situation is somewhat similar to that of Piaget, except of course we talk about a situation involving not one child, but a whole group of children and a teacher. And these situations then in various ways can be designed so that they require the learner to develop his knowledge in certain ways. And this is the, let's say, the central new idea of Brousseau to consider didactic situations as something you can use to experiment new ideas for teaching mathematics as experimental devices, also to investigate more stable, reproducible conditions and constraints for mathematics teaching. Which is different from psychology, because it's a group learning led by a teacher. So that makes a didactic situation different from the situations in which Piaget describes the child as adapting his knowledge to the milieu. Okay, so there was an experimental school in the near Bordeaux, and Brousseau got to supervise more than 50 doctoral students, including students from Brazil in these 2 decades from 70 to 90. So it was hugely influential even beyond France. And in fact, next week there is a conference to celebrate the, I think maybe so some kind of anniversary of Guy Brousseau in Bordeaux, and I think there will be participants from Brazil there as well. Often the theory of situation is presented through the 2 categories of knowledge that are central to the theory. So if we have these 2 triangles, and we are told that we have parallel lines here, click. We have parallel lines here, and we have parallel lines here, and we have parallel lines here. Okay, so now we know something about these 2 triangles. So their sides are pairwise parallel. Okay, and then now we are told that here are the dimensions of the blue triangle. Yeah, it's curious. Yeah, just go forward. No, not go back, go forward. One more, yeah. And then take away the parallel lines. Okay, and then here are some of the dimensions of the other triangle. Every teacher in middle school and many children in middle school will know how to calculate the missing sides there of the red triangle. And it's a very good exercise to think about how you do. I think we all have techniques to do it, but sometimes they are not so explicit. So in other words, in terms of TDS, we will say that we have personal knowledge or knowing in linked to this situation of computing unknown sides in a triangle which is similar to another triangle where we know the dimensions. And this is a word which in French, so in French, and I think in Portuguese also, there are 2 different words for the personal knowledge, so the connaissance, and then the other kind of knowledge. So it's a cognitive phenomenon because we can mobilize this knowledge when we are in such a situation, but it's often individual and not so explicit, and maybe in fact not always the same. Then on the other hand, we have institutional or public knowledge, which is the kind of knowledge we find in books, like theorems and so on. They are shared forms of knowledge. And I think like in French, there's another word for that in French, namely savoir. So publicly available knowledge, which is justified by publicly available reasoning. These are 2 different kinds of knowledge, but of course, our personal knowledge can be more or less consistent with the public knowledge. And Brousseau then describes a large part or I mean, in fact, the mechanism of teaching and learning mathematics as a dialectics between personal knowledge of mathematics and public knowledge of mathematics. So I will come back to that after showing you an example of a situation crafted by Guy Brousseau to investigate how students' knowledge of similar figures can be developed and adapted to the public knowledge. So here you see, so I think many of you have seen it, it's a puzzle, and students are given a real puzzle with these dimensions in centimeters. In fact, they are given, they are organized in groups, and every group gets a copy of the puzzle, and every group must then enlarge the puzzle, so make it bigger, but in such a way that the side there, which is 4 centimeters, becomes 7 centimeters in the bigger puzzle. Yeah, so the students are also handed out paper and scissors and rulers, whatever tools they are usually having, and then asked to construct. Each group must then construct a new puzzle which is larger, and where this side, which is 4 centimeters, is now 7 centimeters. Okay, so that depends, but this is a situation experimented generally in 5th grade, and it turns out that students' first reaction is inevitably to add 3 centimeters to all sides, and then of course they realize the bigger puzzle cannot be assembled because the pieces are not similar to the original figure, and then they will, in ways that is stipulated in the situation, I try other strategies. The key thing is actually to think about what should happen to 1 centimeter. If 4 centimeters become 7 centimeters, what should happen to 1 centimeter? And then you realize that 4 centimeters is 4 times 1 centimeter. If that should be 7 centimeters, then the enlargement of the 1 centimeter should be, when you multiply it by 4, it should be 7 centimeters in order for this to fit, and then that leads, of course, to a multiplicative model of enlargement. So this is often called a fundamental situation for the knowledge about enlarging figures. It is impossible to adapt to the milieu without that knowledge, and if we think of f of x as the length of the magnification of a piece of length x, then the fundamental condition is that that function is additive, because if we take a piece and divide it in 2 pieces, then of course it shouldn't matter if we magnify the 2 pieces together or one by one. So, and that condition is actually enough with continuity to ensure that the magnification becomes a linear function. So that almost ensure unique solution when we add continuity. You notice here very characteristic features of the situations experimented by Brousseau, the very strong feedback you get from the milieu or from the elements of the situation. It's actually enough to validate solutions, so the students can see that if they magnify the pieces by adding 3 centimeters to all sides, that doesn't work because the pieces don't fit together, for instance. And it also illustrates the central idea of Guy Brousseau of the situation as a model of a piece of mathematical knowledge, the model of a mathematical knowledge which is relevant to teachers, because it is what the teacher needs to present the students with in order for them to adapt their knowledge and become consistent with the public knowledge. And this is also what he calls the inverse problem of didactics. So you begin as a mathematician. So he compares a little bit the teacher to the mathematician, but doing the inverse of a mathematician. So a mathematician works with a problem and crafts a personal solution and then publishes it or decontextualizes it and becomes public knowledge. The teacher, on the other hand, does the inverse. The teacher begins with public knowledge and then must create a situation, a mathematical problem in a context, in order for the student then to adapt. Then the student does what the mathematician does. He adapts. The student adapts his personal knowledge to the situation, like when working with this puzzle situation. And then finally, the teacher must also, so besides constructing this, he must also re-decontextualize the personal knowledge. So declare public knowledge what was found by the student in the situation. Okay, so this is was a brief glimpse of TDS, which is still a very lively research program in France, very central also in French teacher education, but perhaps not quite not so well known outside of France, more well known outside of France and French-speaking countries than the German Stoffdidaktik, and less than the last program that I will present to you, which is also the research program I work with most of the time, namely Chevalin's elaboration, the anthropological theory of the didactic, which is indeed an international research community now with active researchers in many, many countries, including Brazil. And I can see I'm now a little bit short of time. I don't know, Aluska, can you just remind me how many minutes? Do I have 5 minutes left, or how much time do I have? And maybe I can't hear you now. Is there anything? Okay, so you must stop me when time is up. But I plan using maybe 5 to 7 minutes to introduce you also to this more recent ideas in French didactics of mathematics. So created by Chevalin in the 1980s and later becoming known as the anthropological.
You already have 15 minutes, don't worry.
So I have another 10 minutes or so?
15?
15 minutes. Okay. Oh, great. So I don't have to rush. Great.
Yeah, don't
Yeah,
rush.
I was a little bit worried if it was 1 hour with. Okay, so
No.
no problem. So that's fine. That's perfect.
Okay.
Okay, so coming back to the slides, maybe so just change to the anthropological approach. Yeah, go forward. Right. So this is then kind of an elaboration or development of the theory of didactic situation, which is, I would say, manifestly extending the perspective of the theory of situations. It's not so much an alternative, but more, let's say, larger perspective on the problems related to mathematics teaching, viewing mathematics teaching as something that occurs in institutions and is an institutionally conditioned human activity, also meaning that mathematics itself depends on the institution in which it is developed. So more generally, knowledge is produced, communicated, learned, and used in institutions, and it does not exist elsewhere. So there is, contrary to what we sometimes make believe or maybe implicitly assumes, even mathematics can have very different forms in different institutions. And this is, of course, also the basic idea in didactic transposition theory that I will come to now. So the conditions and constraints imposed by institutions are crucial for didactic systems. So school institutions are a specific kind of institution in which mathematical knowledge is produced, communicated, learned, and used. So actually also produced. And then the specific conditions and constraints are crucial to understand what can be done about mathematics in a given institution, including in schools. So there's then this idea that knowledge can be transposed, but not simply moved from one institution to another, because the knowledge will have to be adapted to the conditions and constraints imposed by the institution. So when we have knowledge and practice, in particular mathematics and knowledge and practice in society, in scholarly institutions and so on, we can attempt to teach that, but when we teach it in schools or in didactic systems, sometimes symbolized by a triangle, we don't just move it into the school, but it will change, and sometimes change in ways that are hard to predict. So this is also why even Rousseau says that the didactic transposition is something we must study and survey, as he said. So of course it has its usefulness, because it's what makes it possible for mathematics to be transposed from maybe scientific institutions to school. So that's a very useful mechanism. But there are also inconveniences like the various defigurations or reductions that knowledge may undergo in the process. And it's actually useful even in the construction of mathematics. So I mean, there would not be mathematicians unless we could keep educating new mathematicians. And so it's not just about school mathematics, of course, that this mechanism is relevant. And it's at the same time, as Brousseau says, inevitable and necessary. So we cannot have future generations learning mathematics without transposing mathematics to schools, for instance. But it's in a sense also regrettable because of the changes that can occur, sometimes huge reductions and as I said, defigurations. So we must keep it under surveillance. We must study it in a way that doesn't assume naively that the mathematics taught in school is simply a kind of baby copy of mathematics in other institutions, including scientific ones. So this is perhaps sounds a little bit theoretical, but it means that we have to have we have to adopt a more explicit study of how mathematics differs in institutions. And this is in fact the theme of didactic transposition. I know the book by Chevalard on didactic transposition became hugely popular very quickly in Spanish and I believe also in Portuguese. So it's probably very well known in your community. And I just remind you the idea. So the idea is of didactic transposition is that we should study how knowledge travel from outside of school and all the way to the students. So as I said, we have mathematics in institutions in society, including scientific institutions, where it's created, maintained, developed, and used in many ways that go very far beyond what can be represented in school. Of course, then society makes some decisions that some of this should be taught in school institutions. We all know why, in order to prepare students both for life and for higher education in many fields. So society decides what, when, and why to teach mathematics. So that's a completely new part of the didactic study to investigate the procedures through which mathematics outside of school is processed and declared to be taught in schools. So that then becomes official knowledge to be taught. These are documents. I mean, we can study that through documents like laws, syllabi, textbooks, and so on. And we will then see that certain parts are selected. There's a certain structure perhaps also given, and certain aspects that are emphasized and so on. But this is of course only the beginning. There's a long way still to the student. So to didactic systems with teachers and students in them. And this is then the second transposition where other changes and choices and so on may occur, is the internal didactic transposition. And this is the traditional subject of mathematics education research, didactics research, how to teach a given piece of knowledge. But then what is the originality of ATD is to insist that this depends so crucially on the external didactic transposition. So it can be, so sometimes let's say problems or malfunctions in the internal didactic transposition cannot be fully or properly addressed without looking at the external didactic transposition as well. It's of course not a coincidence that this model became so popular in the 1970s after the new math reforms, because this was largely changes in the external didactic transposition. And so the problems that were seen in classrooms with students and teachers and so on could not be solved just by investigating how to teach this new math, but it had to be studied more deeply, the roots of these problems in the external didactic transposition. Okay, so then of course comes the problem, how do we, because there's mathematics in each of these three boxes, so how do we study these different forms or transpositions of mathematics? And this is then where another genial idea of Chevallard comes in modern research. So we model mathematics. We make explicit models of mathematical contents using the theoretical idea of praxeology. So this is a word created from Greek praxis or practice on the one hand, and on the other hand, logos or discourse, words. So we think of mathematical activity as having certain components which may differ from one institution to the other, and which we specify in terms of these two parts, the practical block. So that is essentially what we do when we in mathematical activity. So we have tasks or types of tasks that are solved by certain techniques. And then on the other hand, we have a theoretical discourse about that doing or that activity. That's what we call the theoretical block. That's where so that's of course also central in teaching, not just doing problems, but also explaining and justifying ways to solve larger chunks or types of tasks. So that can be further subdeveloped than the practical block in type of tasks and techniques. So that means families, types of tasks that can all be solved by the same technique. That's of course also a very characteristic feature of mathematics, that we usually have an infinity of tasks which can be solved by a given technique. So this is all the doing, and then we have the discourse that explains the techniques, the technology, and the unifying discourse, the theory, which justifies the technology. So those are the building blocks in ATD models of mathematical activity in modern research, but also I think for many teachers a very useful way to think of mathematics, that there are these 4 different levels, and of course there must be practice. We cannot just teach theory, but theory is also very often necessary in order to refine and justify a practice. Okay. Very last slide before I begin to end, so I will jump over this. More recently, a lot of design research has been done to in relation to the idea of study and research path, which is the idea that you teach mathematics beginning with generating questions to counteract the tendency that there can be in mathematics teaching often to just present monuments of works that are visited but not really used. So this idea of study and research path is to organize mathematics teaching as a sequence of questions and answers connected through those processes of study of works and research or inquiry. And it's often represented by such a QA map where you have the generating question on top, and then this is a model of what how the teaching could develop, beginning with a generating question. I will give you an example in a moment, and it's actually a model that is very useful to teachers and is often used in teacher education based on ATD as a tool for teachers to plan teaching based on such a typically relatively large and open question that allows for the formulation of sub-questions, derived questions, and so on, and eventually the development of mathematical praxeologies motivated by serving this to develop a solution to this larger question. Just a very simple example from one of my own students' thesis. This could be a generating question: how many people have ever lived in the world? It's a big question. It's a classical question in the field of mathematical demography, so the study of how populations develop. I don't know if you have an idea of how many people ever lived on the Earth. It's about 120 billion people. So how can you find out about that? So it's a real question, and students in high school can actually investigate it both through study of works, inquiry by themselves, and ideas like cumulative growth, integration, infinite summation that they actually meet in high school. So here's a picture of the rough development of the world population, but this is of course just a fictive graph. What we have are a few points through the human history, estimates of how many people there were. So how can you from these finitely many points generate an estimate of how many people ever lived? This is the topic of this particular study and research path, generated by the question that you see there, and it's then a priori analysis, or the analysis or the plan of the teacher with anticipation of what teachers could do in terms of a QA map, and then also a posteriori analysis based on observations. What did students use and produce that can lead to refinement also of our design of the study and research path. Okay, this is what I will say about HCD, and now finally I will just to close compare the three research programs. So sorry. Yeah, so move to 5. We have these. I've briefly introduced you to Stoffdidaktik, the theory of situations, and HCD. The French didactic is aimed mainly at fundamental research on the main mechanisms, conditions, constraints, and so on of mathematics teaching and learning, while the German Stoffdidaktik is grow out of the purpose of contributing to curriculum development and teacher education, and has a huge impact in Germany. So that makes them quite different in actual original purposes. They are also different in method. So Stoffdidaktik is mostly a mathematical activity or research program. It's at least very central part is mathematical work, while TDS and ATD are more, let's say, experimental educational research. There's also different degrees of international presence that is written there in the table. So Stoffdidaktik is mainly known in the German-speaking world, TDS mainly in the French-speaking world, and ATD more internationally, and so on. So we have a paper in one of the last issues of Educational Studies where we, with Hochmuth, Peters, Rönning, and myself, developed this comparison of research programs. And then I promised to close off with a very brief introduction to the European Society of Research in Mathematics Education, founded in '97 in order to promote dialogue between the different forms of didactics in Europe. It's an affiliate organization of ICMAE, holds conferences like CERME and so on, and welcomes, in fact, scholars from all over the world. The next conference is in Bratislava, Slovakia next year, and I warmly invite all of you, although I'm not the president of ERME anymore, but still we welcome you and everyone to attend the conference. You can have more information about this society at this website, erme.site. So thank you very much.
Thank you, Professor Winslow, for the excellent conference. Agora eu vou tentar fazer uma breve síntese das ideias apresentadas pelo professor Winslow na conferência de hoje, que tem como título traduzido, então, Estudando e Desenvolvendo o Ensino da Matemática através da Pesquisa, 2 enfoques da Europa. Inicialmente, o professor Cal cita alguns marcos históricos relativamente à institucionalização da matemática na Europa, destacando que a educação primária obrigatória foi estabelecida primeiro na Alemanha, em 1717, seguida de outros países europeus. À época, a matemática compreendida pelo currículo, então, compreendia aritmética e um pouco de geometria. O ensino secundário, que denominamos no Brasil ensino médio, foi democratizado aproximadamente uma década após a institucionalização do ensino primário, conforme mencionado. Nesse movimento, o professor Cal cita outro importante marco histórico, que se refere ao programa, então, material didático, proposto por Felix Klein, matemático alemão que viveu entre 1849 e 1925. O professor Cal destaca inicialmente que a pesquisa e didática da matemática surgiu da necessidade de formação de professores para ensinar matemática. E esse é um aspecto importante da conferência de hoje, porque sinaliza o despontar da pesquisa e formação docente, relacionado, então, à formação de professores de matemática. Assim, o professor Winslow inicia abordando a origem e os desenvolvimentos desse programa material didático, ressaltando a contribuição, então, de Felix Klein, que deixou um importante legado para a didática da matemática global. Felix Klein, que é autor do livro traduzido Matemática Elementar, de uma perspectiva superior, publicado em 1908, já problematizava a formação de professores, chamando a atenção para o gap entre a formação matemática recebida na universidade e a matemática a ser ensinada na escola secundária por esse futuro professor que recebia, então, esta formação. Que é uma questão que permeia mesmo as discussões no âmbito da educação matemática, inclusive no Brasil. Klein considerava que os cursos de matemática avançada não eram suficientes para formar professores de matemática para a escola secundária. Propôs, então, um programa material didático como parte integrante da matemática na universidade. Com a reforma da matemática moderna, introduzida nos anos 1960 no contexto europeu, tal como ocorreu também no Brasil, foram introduzidas algumas mudanças, que foram bastante significativas no ensino da matemática. Nomeadamente, então, como chamamos aqui também, a introdução do método axiomático baseado na teoria de conjuntos. A partir dessa reforma, foram criadas várias escolas europeias de pesquisa em didática da matemática. E foram, com isso, então, modificando os processos e as discussões e a pesquisa em torno desse tema. A partir de 1970, o programa Material Didático de Klein sofre algumas modificações, passando a assumir um objetivo um pouco diferente, de apoiar o desenvolvimento curricular da matemática e, sobretudo, a formação de professores de matemática. Também em 1970, em face a esse movimento denominado Didática da Matemática na Europa, o francês Guy Brusseau inaugurou a Teoria das Situações Didáticas, TSD. Essa teoria preconiza que a aprendizagem da matemática ocorre mediante situações didáticas, então, tendo ou centradas em conhecimentos matemáticos, que funcionam como dispositivos experimentais para investigar as condições e restrições para a aprendizagem coletiva e dirigida pelo professor de matemática. Então, aqui temos outros elementos relacionados à discussão em torno da aprendizagem da matemática e que atravessa também o ensino. No âmbito dessa teoria, 2 categorias de conhecimento foram destacadas como centrais. O conhecimento situacional, relacionado à pessoa e à situação didática, e o conhecimento institucional, que refere-se à forma geral e institucionalizada pelo qual esse conhecimento é compartilhado, socializado. O professor Cal ainda nos apresenta a seguir a teoria antropológica do didático, proposta por Yves Chevalard, fundada aproximadamente em 1980. No âmbito dessa teoria, Chevalard estabelece a teoria da transposição didática e a teoria antropológica. Apresenta-nos, assim, um modelo de transposição didática, explicitando o modo pelo qual o conhecimento viaja da ciência para o aluno. É o modelo apresentado, então, no slide 15. A seguir, o professor Cal apresenta um modelo de estudo e pesquisa elaborado a partir, então, da teoria de Chevallard, sistematizado no mapa QA do slide 17. Ao final, apresenta um quadro comparativo entre os 3 programas de pesquisa presentes no contexto europeu, nomeadamente material didático, teoria das situações didáticas e teoria antropológica do didático, das quais destaco aqui nessa síntese os objetivos de cada um desses 3 programas. O material didático, então, tem como objetivo principal o desenvolvimento curricular e a formação de professores. A teoria da situação didática tem, então, como objetivo central a pesquisa fundamental, do mesmo modo que a teoria antropológica do didático. Apresento também outras especificidades de cada um desses programas. Por fim, o professor Cal destaca o importante papel da Sociedade Europeia de Pesquisa em Educação Matemática, ERME, por meio das suas ações, especialmente o evento CERME, que tem ocorrido continuamente. E nos convida, então, para o 15º CERME, que será realizado em 2027, em fevereiro de 2027, em Bratislava, na Eslováquia. Iniciamos, então, agora a plenária com as questões dos participantes, ampliando esse debate, o qual será coordenado por Aluska, que já está aqui conosco.
Obrigada, professora Adriana. Now we are open to questions. Vamos começar com a primeira pergunta. A pergunta é da professora Regina Pina. Integrating mathematics teachers into education activities that are collaboratively constructed and developed by universities and schools is a major challenge for many Brazilian regions. How have they experienced this challenge in Europe, and how has research built bridges?
Can you hear me?
Yeah?
Yes, good. So actually, some of the institutions I mentioned were like the Institute for Research in Mathematics Teaching that were set up in France around 1970, were set up with the purpose of promoting the collaboration of so university researchers and teachers. I'm not saying that they always do so in very efficient ways, but there are like institutions that are set up to further such collaboration. So also for teachers to participate in seminars and research and so on with university people. But this, of course, touches also in France and similar institutions in Germany or even Denmark, a small minority of teachers. So I think it is a problem we share, that there can be quite a distance or from new ideas being taught and developed at the university, in teacher education, for instance, and then being implemented or used and known in schools. So this is let's say an institutional challenge we share, but it can always be interesting to see how this is organized in different countries. I think, in fact, this is one of the main interests also of lesson study in Japan, that university teachers are sometimes much more directly engaged in, let's say, teacher development in actual schools. So there can be many ways to organize it, but let's say it's a shared challenge. All I can say is we can learn something from looking at the institutions of other countries and how that challenge is addressed. But so I'm not sure. Well, I would say perhaps also that in Germany the connection is somewhat, like in Japan, somewhat more direct, because Stoffdidaktik and German didactics is, so for instance, it's very common that German didacticians are also involved in textbook production, which I think is very rare in France and many other countries. So there's, of course, also a little bit of dilemma between research being very much involved in professional development and curriculum development and so on, and the ambition that is very central in the French tradition, that didactics should be a scientific activity. That there should be development of knowledge which is not just valid now and here, but universally valid. So that's it's also a little bit of a dilemma in universities, because universities are generally, let's say, expected to develop new knowledge, which is not just knowledge of some individuals, but knowledge that can be shared and used everywhere. So that is a dilemma. But let's say this continuity, if we are optimistic, between schools and research is a very interesting phenomenon that plays out very differently in different countries. That is why we are so. I think one of the reasons we are so fascinated by Japan, that they have a very different way to organize that interaction.
Thank you, Carl. A tradução já foi bem próxima do que o professor Carl falou para a gente, e ele enfatiza não só a didática da matemática francesa, mas também traz o exemplo do estudo de aula do Japão, que eles têm essa grande aproximação entre os professores e os pesquisadores desde há mais de 100 anos. Então, vamos para a próxima pergunta. Next question. O professor Tiago asks, this approach can leave teachers feeling unconfident in the sense that they don't have control over everything that might come up in the classroom. It's a teacher education project. How can we bring teachers close to the basis of this knowledge?
So, of course, there are three different, or at least two different, very different approaches, the German and the French. So I think and also, of course, that now I was mainly talking about research in France and research in Germany, but it is also associated with this problem of let's say, bringing research to schools and to teachers, and teacher education is, of course, one way. I think it's also important that education is not in a profession is not something that is limited to the time before you assume the profession, but again, we need organizations to make sure that teachers are also continuing to develop professionally, and so maybe it comes a little bit back to this question of how to connect teaching in schools better to research at universities, and different ways can be there to organize that. But of course, the teacher cannot control everything in the classroom. So I think, like, I'm not sure exactly what the colleague thought about could make teachers feel somehow at a loss because they don't control everything. But so I don't know at what moment this idea came up, but it's clear that many of the designs, like the puzzle situation and so on, are not set up in order to be models of how to teach, but they are set up to investigate the mechanisms of teaching. So if that was the moment where this idea come up, maybe I should have said more clearly that Brosseau's experimental situations are not meant to be a model of what mathematics teaching is or should be. It's a way to investigate what happens in mathematics teaching. Then, of course, the idea of situation and some of the theoretical ideas also in TDS can also be important for the teacher who meets them in teacher education or elsewhere. So, for instance, one thing that from TDS that I think is really useful to teachers is this idea that are very different parts of didactic situations, like the devolution, where you present a problem the formulation of solutions by students after some level of action also, and then above all the situation of validation, which is often forgotten in schools, where you deliberately work on evaluating the goodness of the various student solutions that come up. And of course, having this dynamic also presupposes that teachers continuously develop and reflect rich situations that are not just like one-line answer questions, but contain rich problems. So this is of course something where inspiration can be taken also from research, but not from not in the sense that you should simply copy specific situations like the puzzle situation. So research can never be expected to develop, let's say, ready-made curriculum or teacher-proof curriculum. The teacher is a necessary part of the internal transposition in the terminology of ATD, and do not consider the examples from research as more than thinking tools, not as models of how teaching should always be.
Thank you, Professor Carl. Gostaria só de complementar aqui que, olhando para o nosso país, a gente tem a oportunidade de receber estagiários na escola, receber PIBidianos, e essa é uma forma de aproximar também a universidade de escola, e desses futuros professores também trazerem algumas bases de conhecimento que eles têm estudado na formação inicial, certo? Assim como dos professores também irem em busca de mestrado, especialização, doutorado, onde eles podem se aproximar dessas bases de conhecimento também. Vamos para a próxima pergunta. Next question from Professor Ana Maria. Professor Ana Maria. In the Mathematics Teacher Education course, are Brousseau and Chevallard theories worked on by the educators? How are they addressed in the initial education in order to link theory and practice?
Yeah. Okay, that's a very concrete question, and I'm happy to answer. Of course, the answer depends on the country. So in France, I think the theory of situations is some elements of the theory of situations are really important to help teachers structure their work with teaching. As I said, for instance, recognizing these different types of didactic or parts of a didactic situation and their contribution to the learning project of a lesson is something that is taught with many examples, also examples worked by the students and so on in planning lessons and so on. I can say also in Denmark, in our teacher education, the theory of situation works in this way as a tool for teachers to think about the different elements of a lesson that need to be there in order to create a more complete mathematical activity. So it's not enough that students produce solutions, but they must also exchange, develop, get tools to validate those solutions. And the final phase, which Brousseau calls institutionalization, is important to connect the personal knowledge developed in the situation with the public knowledge. So students, for instance, get the correct terminology and so on. So I think TDS has a lot of practical uses also in teacher education and in the life of teachers for planning lessons, evaluating lessons, and so on, thinking about the lesson as a situation which they are responsible to launch, to manage, and to conclude. And of course, some of Brosseau's classical situations are also used as exemplars, but as I said, not necessarily as models of how every teaching should be. On the other hand, ATD, we don't teach to teachers, let's say. We teach it to graduate students who are going to make theses in didactics, but it's not completely true. I have a colleague who uses the tool of study and research paths a lot in courses with teachers, especially in-service courses and so on. And also elements of Stoffdidaktik are taught in courses. So those courses will be more, let's say, mathematics for teacher courses. So, but where we teach then elementary mathematics from from this higher standpoint that Klein also recommends. So I think many of these models are in many countries with different degrees, of course, incorporated into teacher education, but of course in transposed forms, so in forms that are adapted to teacher education as an institution. So there's also a didactic transposition at that level. And as I said, it differs from one country to another what is more dominant or common to do. But yeah, I think it can be important for teachers to have theoretical handles on elements of mathematics teaching that can help structure the work, also the work reflecting on experiences from teaching, what went well, what didn't go so well, to share hypotheses about lessons with other teachers and so on. So we have also used some of these theoretical tools in development projects and even European projects on teacher development. But it's a really good question how to make these, the outcomes of research useful in teacher education. Really good question that I think we can all reflect on our whole career without reaching a final solution.
Yeah, thanks, Professor Kaur. Adriana? Now we are finishing this webinar. So we are grateful for you to be here and for your talk and your answers. Thank you very much, Adriana.
Pleasure. Thank you. Obrigado.
Obrigada. Agradecemos a todos os participantes que nos acompanharam nesta tarde. Agradeço em especial ao professor Winslow pela conferência e pelas reflexões provocadas. E agradeço também à Aluska pelo trabalho desenvolvido e desejo a todos um excelente final de semana. Muito obrigada.
Obrigada.